Hey everybody, this is Negative Light here, back on a journey to a Redstone computer. Now you might be a computer engineering student or a Redstone engineer wanting to make a Redstone computer but don't know which gates to use, and you're getting tired of writing these giant truth tables for 8, 10, or 20 bits. Well, today I'm going to show you something called a Kmap. Now this right here is a Kmap. It is a very simple representation that takes advantage of something called logical adjacency. And as a note, for those of you who are watching this outside of a computer class, I'm going to be referencing bits a lot today, and that's just because it's an easier way to say this, but it works for any form of logical statement. What logical adjacency talks about is something being only one bit difference. So for instance, right here, this only has a 1-bit difference between these. So anything beside these two, beside each other, will somehow be connected. And it only works with powers of 2. So for instance, something like this, that won't work because there isn't logical adjacency. But right here, you'll notice, right here, this group of 2 can be represented with just 1 bit, the green being on, or this right here shows that these 2 bits can be shown with the blue being off. And that's kind of what a Kmap does. Now, how do you use these? So first off, you're going to want to select what you're wanting to look for, when something's off or when something's on. Some cases, it might actually be easiest, for instance here, to tell when something is off. Now today, we're going to be focusing on when things are on, but you could also just sit here and look at it and say, oh, well, I've only got these 2 things, and so if I look for what I don't want, it might be easier. Nevertheless, we're going to continue. So first thing is you're going to take the highest group of some power of 2. And note that these are on powers of 2. So for instance, you have 2 groups of 4, so that's 8. So the highest you can have is a group of 8, but obviously you could have 2, you could have 4, or you could have 1. So you're going to take your largest groups first. So for instance, right here is a group of 4, and then you're going to see what doesn't change. So going all the way down, both the green and the blue inputs on this one change, so only this dark green which stays on. So you'll put that down and you'll say that's on. So green on, or just green, however you want to say that. And then we're also going to use another block. This is just used to represent an OR. And that's just for ease. Now we're going to look at these other 2 and you'll notice, okay, so across this group of 2, the green changes, but the lime and the lime green and the light blue do not change, and they are both on. So we'll grab both those and blop, bloop, and on. Okay, and the same thing for when they are off. So we'll place another OR and light blue, light blue, lime green, and we can place those both being off. So this right here, if you wanted this specific set of inputs, would read as being dark green on, light blue, lime green being on, or light blue, lime green being off. What type of circuit would you call this? I would probably think that this is some kind of like equivalence or equality detector that also checks if with like some kind of override. So this being your override, and then, oh, okay, these 2 are equal, so more than likely this is the gate you want. And there are other ways to build this that you might see in a video later. Now, let's go on to why you would really use these, because really at this small of a level, it is useful. But, I mean, not quite so much. So right here is the actual kind of typical use case. And this is where I want to make a note of why I'm building it in this specific pattern. Notice I have these large strips of crimson. This is because you'll notice these flip right here. And that's because if you notice, if we change this from the orange being off and the light or the dark green being on to them basically flipping, 2 bits change. That means that they're not logically adjacent. They can't connect. So that means that when you're building one with a set of 4 bits, which is the highest size you can go for a single column or row, you're going to have to go 1, 2, so a group of 2, then you're going to split it, and then a group of 2. If you're doing this on a notebook sheet of paper with me, I would suggest doing it this way. Start by drawing a quick box. Then you're going to take and you're going to just put maybe like an angle somewhere and put your input names. So for instance, the one that I'm drawing today has a and a B, and then a C and a D. Then I'm going to start by going 0, 0 on one of the sides. So I'm going to start on C and D, so I'm going to go 0, 0, then I'm going to put 0, 1, and I'm going to draw a line. That just tells me that I flip. 1, 1, and then 1, 0. That's going to cover all of the cases. And we'll repeat that pattern for the AB. 0, 0, 0, 1, long line going through, 1, 1, 1, 0. And then you can also draw like smaller lines and stuff that just to help you kind of navigate it if you're doing it on paper. Now, why I suggest you also learning how to do this in Minecraft is because, well, you have to wait for the bonus, I guess, which you'll see here shortly. And also, if I cannot get those things drawn on the image for you or on the video for you guys, I am very sorry. I will try to come up with a way to start doing things like that a little bit more frequently, because I do think that that helps with this specific type of video. Now, the last thing I'm going to show you is how to do this for 6 bits, which is where Minecraft is rather unique. So you can do 6 bits in the real world by taking 4 of these truth tables and then setting them side by side and then repeating that pattern that we did for A and B, but instead labeling them with other inputs such as A, B, C, D. So we'll do E and F, right? So you have E and F, and so one of them is for the 0, 0, one of them is for the 1, 0, then you'll have 1, 1 right below that, and 1, 0, or 0, 1 actually. And those will kind of form a box, and you'll notice if you look at them, each row goes over one. It has a 1-bit change, so they'll be so the 0, 0 and the 1, 1 need to be diagonal from each other, and the 0, 1 and the 1, 0 need to be diagonal from each other. That just works with the logical adjacency, and then anything can cross between those two. So this is also here to kind of show you one of the oddities of this. Look right here. Notice how this, when the black and white, which is what the third dimension of this is, look at this back area. You'll notice that the first input, 0, 0, and the last input, 0, 1, are logically adjacent. So things can wrap around. So for instance, so this is also here to kind of show you one of the oddities of this. Look right here. Notice how this, when the black and white, which is what the third dimension of this is, look at this back area. You'll notice that the first input, 0, 0, and the last input, 0, 1, are logically adjacent. So things can wrap around. So for instance, if this corner was completely full and this corner was completely full, that actually is one group. And so you can count it that way. It's pretty unique and really interesting. So just keep your eye out for that. Remember, with logical adjacency, things can wrap around your entire table, but it can only go from side to side. So just keep a note of that. And sometimes it might help to maybe rewrite it with a different format. And the output of it comes out a little something like this. Another interesting way to kind of tell if you missed something is the same mistake I made a little bit earlier today when prepping this lesson. Was I noticed that my white here was both on one of these, and if you look at, and then we also had the lime green, the orange, and the black being off once again, but with the white being on, or off and on. So blop blop blop, and the white being on, or off actually in this one. So notice that these two right here are equivalent only by this 1-bit difference, and it flips. Well, I mean, if you really looked at it, and I will hopefully be able to do a lesson on Boolean algebra very soon. I really want to do that because I think it'll help you guys really improve your survival logic builds. But notice how you could just group these, right? This could be one thing, and that, and then OR it with, and it with this, and you'll notice that that's one. That's always going to be on, so we can just get rid of all this, get rid of that, and just look for this. And that's kind of the cool part about this. Now, today, for the bonus of this video, I also wanted to show you how this is really, really helpful when you want to build an 8-bit computer. Remember how earlier I mentioned that you can build a 6-bit Kmap on a sheet of paper by taking our 4-bit Kmaps, right? The little boxes with just these inputs, kind of like this, and then putting one, and then setting them side by side with and labeling them with a set of inputs, for instance, E and F, when you have A, B, C, D. Well, you can do the same thing right here. Look at the top of this table, and you'll notice that I have a red wool and a yellow wool. Well, that could be for when those two inputs are off, and this is just that specific Kmap. Well, now I could go and build another set of 4 and have this pattern repeat. I don't have world edit, so I just don't have the time in my life to do that right now, and I'm so sorry. But that means that you could, for any of the components of an 8-bit computer, build a Kmap in Minecraft for it and be able to tell exactly what you want to do. So, for instance, if you wanted to tell when something's going to happen, build it that way. Obviously, we do try to kind of keep a consistency throughout our builds, and the Minecraft community has actually developed kind of this general, like, this means to add, this means to subtract, or, you know, you're going to look for this to do X and this to do Y. So you're not really going to have to look for it, because a lot of times we're pulling from each other's builds and working together, which is a wonderful and majestic thing. But it's still also cool that you can build these things and be able to go larger and look at new ways to do something, because you might notice that there's just this iota, something slightly different that you can do that could improve the efficiency of a computer tenfold. And I'm really looking forward to the new shulk sensor, because that will open the doors for new clocks, for new machines, heck, for new ways of communication, because now we could transmit a signal without a single redstone line. Which means that inside of your tightly packed machine, you could have a binary input using wall occlusion and stuff that is vertical, horizontal, and does some really cool things. But nonetheless, I really hope that you guys enjoyed this video, and I hope to see you again soon. I'm hoping here pretty soon to maybe get a server with my friends where I will be continuing the Logic Island concepts and actually showing you guys how to build some serious gates and machines. But without further ado, this is Negative Light signing out, and God bless y'all. I'm about to die. Ow. I gotta stop dying, y'all. I really do.